Okay, I think we'll get started. So today in the lab we're going to do a little bit more with UART, Universal Asynchronous Receiver Transmitter. We're going to read in a character, an ASCII character from the computer, so we'll just use PuTTY in this case, working on a Windows machine here. And we'll store that in one of the memory registers of the PIC10F200. Then we will indicate with an output whether we have received an uppercase letter or a lowercase letter. So this gives us the chance to read, store, and then do something with that stored result. What we'll learn here is just rudimentary bit banging, and so that's when you use the software to interpret the signal coming in from the UART or vice versa going out. We're not going to do any writing out back to the computer on this lab. And we'll get a little bit of familiarity with the ASCII characters. So in general here, the UART works by holding high, and then it sends a start bit, and then the 8 bits of data, and then a stop bit. So there's 10 bits total, and we want to key in on this 8-bit region. 8 bits is enough to encompass the ASCII characters, and it's handy to print out. Online you can quickly find a table of ASCII characters. It's nice to have that printed out and ready for you when you're working on this. A couple of good test characters that I've liked to use is capital U is 010101, so that's kind of a nice sequence. And then lowercase u is the same. And so you can get a sense for when you see this on the oscilloscope, what direction is what, and what bit is what, how wide the bits are, and so on. Another important one is space. So that's 001000. And the reason this is important is we're going to use this in this lab to key in on the characters. So if we look in general at the ASCII table, uppercases are 101 or 010, and then whatever their code is over here. And then the corresponding lowercase is 011, whatever their code is. So we see here is, these are identical because it's capital U and lowercase u. And so whatever these are for each of the individual letters in the alphabet, these will correspond to the same values. And so we can use this bit for the goal of our build today, and that is to output whether we have received from the computer a capital letter or a lowercase letter. So we'll be able to key in on this this bit right here. So bit 0, 1, 2, 3, 4, 5, 5th bit over. Just for completeness, although we won't use this today, the numbers 0 through 9 are 0, 1, 1, 0, and then the last 4 bits are the binary value for this 0, 1 through 9. So 0 is just all zeros the rest of the way. 1 would be all zeros and a 1 right here. 9, of course, would be 1, 0, 0, 1. And so this is how the numbers are encoded. So lots of times we might be interested in receiving a number from a computer, then we read off this last four digits, or 4 bits. All right, so we'll go to the board. I'm going to have to do some little more fancy footwork with the camera because we're going to be looking at the oscilloscope as well. But first we'll take a look at the code, and then we'll look at the action both on the oscilloscope and on the breadboard. So here we are with the code, and the initial part here is that regular stuff about the configuration bits. So turning off the watchdog timer, turning off the master clear, bringing in the include files for the PIC10F200. This is setting the reset vector and telling the program counter to start at main. Then we go into the structure of our program, and as before, always trying to do the same throughout this whole series, and that is in the first part of the main we put in the settings to set the outputs and inputs that we'll be using. In this case, we're only going to be using GP0 as an output, and then we're going to be using GP1 as an input. So these are the two digits here, 1 as an input, 0 as an output. And then tris6 writes that to the tris register. This we don't need at all, but I just leave it here as part of our boilerplate. And this is dealing with pin 2, which we're not going to be using. All right, so we enter into the main loop, and we're just by default we're going to set the output to 0. And so sort of the opposite of which the UART is. That starts at a high and goes low. We're going to start low and go high. Then we'll make 2 counters, and we're going to use 9 here because we have to account for the stop bit. So we don't want to include the stop bit, so we're going to run this 9 bits over and drop the stop bit off the end of our memory. The memory will be, where we're storing it will be in 1.7. So memory 1.6 and 1.5 are going to be used as counters, and memory 1.7 is going to be where we're storing our information. So as a precaution, we're just going to clear that. I think it's probably cleared when the program starts, but we'll clear that. Then we enter just polling loop, and we're going to poll GP1, and notice here skip if clear. Now remember, with the UART we're starting high, so this is always going to be high. We want to keep polling that, so we want to stay in the loop until we get it clear, until we get the start bit signal. I throw in a few no operations just to slow things down just a little bit. We want to be off the edge of that rise, and so we're going to just shift things by a little bit. Doesn't take much, and everything seems to be works robustly. You could put a little delay here, but I think this is enough. Now we're going to go into the read loop, and so we're going to be reading GP1, and this set of commands here is just checking to see whether we're set or we are clear. So we're going to check GP1. We're going to skip if we're clear. So if we're not clear, we're set. So that means we're going to set bit 0 of 17, and then we are going to check if it is set. Well, it is set, so that will skip that and not clear that. Likewise, if we were set, then if we're set, we'll not skip this, and we will set this, and then since we're set, we'll skip this and we won't clear this. Then we're going to rotate. So we've used this strategy before. We're going to rotate the memory 1, and this is a very convenient way of writing in bits because we can do it in a loop now. We're just going to slide this over each time. Now we've first written in the and then we're going to put a little delay because we have to match the UART signal coming in. And I just did this empirically. I just experimented with different baud rates for different delays. Certainly you could calculate things more precisely, but for our purposes, we're just going to, again, just pretty quickly figure it out experimentally and then just use it. So we put a little delay to skip to the next bit that the computer's writing. So we can't just sample right away. We have to delay, sample, delay, sample, delay, sample. And then we decrement the first counter. So this will decrement down. And we'll go 9 times, so that'll send that stop bit off the end. And we will have the 8 bits in the memory register 17. So that completes the writing of the data to the memory. Now we want to well, this is strictly necessary, but we're going to put this in there so we can see this on the oscilloscope. So if all we were worried about was determining whether this was an uppercase or lowercase, then we wouldn't need this part. But what I'm going to do is spit this out to the oscilloscope on a second channel, and we'll see that we are seeing the correct ASCII character in the memory. So just sort of the opposite of what just happened. We're going to now read from 1.7 and set GP0 as appropriate. And so again, this is a common thing to do here, this set of 4 commands to get the alternative, whether it's set or not set. Then we rotate right and put our delay in. We wouldn't need this same delay, but just for I guess symmetry reasons, we'll write the data out to the oscilloscope at the same baud rate as it came in. And we're using our second counter now, 15. Again, that was stored up here, so we're counting that out. Okay, and then we go into the last part of the program, which is going to identify whether this is a uppercase or lowercase. And just the way the rotation has happened, we're keying in on bit number 6, and then we're just going to put a little over half a second delay, and that will turn the light on if it's a lowercase number, because the bit will be set, and turn the light off if it is or leave the light off, I guess, if it's an uppercase. So that's the whole program here to read that in. I think I've already got it built, but let's build this and then write it to the PIC10F200. Okay. Now what I'm going to do is I'm going to go to black screen. I'm going to set up the screen that's on me actually to be on the oscilloscope, and we'll look more closely at the breadboard and the oscilloscope. All right, so here's a look at the oscilloscope. Now, what I'm going to do off behind the scenes here is I'm going to open up PuTTY and choose our serial port. So we've done this in a previous video, and so to see how to use PuTTY and to talk to the instrument that way, you can watch that. I'm going to set the baud rate. This is just done, I just sort of experimentally figured this out. The baud rate is going to be 3,550. This is certainly not a common baud rate, but it is one that works now for this experiment. So I've got PuTTY open, and I'm going to try to send a character, and you can see it on the screen here. So I'm going to send a capital U. And you see the up, down, up, down, up, down on the screen. And the bottom trace is the directly from the computer. And so we can see bottom trace here is high, and it's going to go low. So let me hit a capital U again. Goes low. And the top trace then is that second part of the program that isn't key to determining whether this is a capital or a lowercase letter, but just helps us see that we're reading things in right. So when I hit the capital letter, we're now going up, down, up, down, up, down, representing the U coming in. If I use a lowercase u, we can see that extra 1 in there, right here, and then it's showing up here. And if I use a space, space is nice because that has just that one bit there. Okay, so let's look at the breadboard now. So here's the PIC10F200. As many times before, these are the wires to talk to the PIC Kit 5 and program it. The wires coming in here are coming from the UART device. And so in a previous video I showed what this was on Amazon. So pretty cheap device, $10. Works immediately on Windows 11 and Unix, I've found. I haven't tried it on a Mac at all, and then I had trouble with Windows 10 to even get it to work. I never did get it to work. There are other UART drivers as well, or devices as well, and so hopefully whichever one you have will work for this purpose. One thing often you can do just to check is if you just jumper these across and open up PuTTY or some other terminal that you can write to the COM port, and then just see if you get a return of whatever you type in. That's what's going on here. Of course, you can't see the PuTTY, but I've got both the transmit and the receive essentially jumper together, set to the same pin here on the PIC10-200. So I can see on my screen with PuTTY what characters I'm putting in. And then these leads here, the alligator clips, are just going to the different channels on the oscilloscope. So let's just give this a try. So I'm going to press notice this on the scope. If you look on the scope, this is the lowercase u, and we are indicating with the red light, or the LED on, that this is a lowercase. Now I'll do uppercase U. We see the little flashing. That is just because we've got that second part of the program that is that's putting the output to the oscilloscope. So we are picking that up a little bit, but it's not staying on for this extended period of time like it is for the lowercase. So now I'll just try another lowercase d, lowercase e, uppercase D. Spacebar should turn on because it has the ones in the right, it has that one spot in the spot we're keying in on, as should the numbers. So here's the numbers 1, 2, 3, all turning on. And so this is an example of the ability to write to the PIC from the computer. So this gives the user a little more control over the PIC once it's up and running. And because PIC has a little bit of memory, we can store that in memory and then we can use it. And so in this case, we used it very simply just to determine whether it was a positive or negative value. But certainly you could add it all up, maybe try to use the input to change the output of an oscillating square wave or something like that. So it would give you some user control from the computer. So hopefully this gives you a start on this, and you can do a little exploring for yourself and see if you can get the ASCII characters to write correctly, and then maybe try to do something with them and use your creative ideas to do so. All right, that's it for this lab.